Okay. So, in the last class we started discussion on non-equilibrium field theory, right. So, I took Benjamin equation and we constructed Green's function, correlation function, and discussed briefly about fluctuation dissipation. Now, we will go to, well, that is in fact is a toy problem, but we will do more complex problem today. So, it turns out turbulence is a nice example of non-equilibrium field. Okay. We will have velocity field and that will show you non-equilibrium features, and I am going to tell you exactly which part of this theory of turbulence is non-equilibrium. Okay. And we will keep that in mind. So, okay, we can say we can contrast equilibrium versus non-equilibrium. Okay. So, the one of the most famous theories called Kolgomorov theories of turbulence, and that is what I will discuss today. I will set up the equations, but I will just we will use this as a framework. Okay. So, some of you, well, most of you I think know Navier-Stokes equation, but some whom are not familiar with this, for them this is the equation for the fluid flow in this room. So, use the velocity field, it is not velocity of the molecules, okay, it is a velocity of the collection of molecules. So, it is a continuum field, that means I can write u as function of x and t. So, this is a nonlinear term, u dot grad u is called advective term. So, the left hand side is total derivative d by dt of u, and right hand side is the force, like this acceleration. No? So, Newton's law is acceleration is force by mass, but of course, not a point particle or isolated particle, it is a continuum. So, you have to think of force, local forces. So, gradient force, then external force which could be gravity or it could be electromagnetic force, okay, and the viscous force. Okay, there is a viscous force because of differential in velocity. So, this is the Newton's law, and we will look at the properties of this equation. For this class, or in fact in this course, we will assume that flow is incompressible. Okay, that means the volume of a segment when it moves, it does not change. Okay, or we can think of density is constant, okay, during the evolution. So, there is a quantity which is very important called Reynolds number, which is the ratio of the nonlinear term, this nonlinear term, right, is the quadratic in u with the ratio of this and viscous term. So, it is in fact u dot grad u divided by nu grad square u, okay, and that happens to be ul by nu. Nu is a kinematic viscosity which has units of centimeter square per second. Okay, you can see that ul has the same units as nu, so it is a non-dimensional number. Okay, and the flow becomes turbulent when Reynolds number is around 5000 or more. Okay, there is no critical Reynolds number, depends on the system, but it should be significantly large. Nonlinear term should be much more than the viscous term. Okay, so Fourier space. So, we will work in Fourier space. So, the same equation we can write in Fourier space, right. I mean, I discussed Fourier space many times. So, the Fourier uk is a Fourier transform of u of x. This is a nonlinear term, I am going to write down the expression for that in a while. Pressure gradient becomes minus IKP, this is a force and this is a viscous term, right. The Laplacian becomes minus k squared. In the nonlinear term, it is, you write for nonlinear, for incompressible flows, you write like this, u dot grad u becomes, the gradient can be taken out, it can come out, okay, because the divergence free condition. So, it is this, and the nonlinear term. So, right now I am writing a vector equation, okay, is convenient to write. So, nonlinear term, this becomes a product with the convolution, and that gradient gives you ik. The ik is coming from the gradient and uj ui is coming from here, okay, and of course, p plus q is equal to k. Convolution has this condition, right, so that we discussed that before. So, this is what we get, and the pressure we can determine by the incompressible condition. If I take a divergence of the whole equation, that I can get pressure, or divergence will be ik dot. So, if I do that, I get pressure, which it will come like this. Okay. So, I am going to skip steps In fact, I am not really I am trying to give a quick overview of turbulence. So, to discuss all of it will take time, but we will go fast, but I hope you get the gist of it. So, this is a nonlinear term, okay, Nu, and that will treat as a perturbation when you do field theory. Okay, when you do renormalization group of this equation, then we will treat that as a perturbation. I am going to do it soon, okay. So, you have to just wait for a few minutes. So, we define energy spectrum, it's in fact it is called modal energy. So, given u of k, you can take mod square. So, that are the units of energy, well, density is 1. So, this is called modal energy, every mode has energy and that is the energy, and the total energy will be integral of u k, right. Right now I am going to sum it up. So, this integral is the total energy. We can write down equation for the modal energy. So, from the Navier-Stokes equation we can derive it. So, I wrote the equation for d by dt of u k. I can take a dot product of this with u star of k, okay. Then add it to complex conjugate plus complex conjugate. So, that will give me d by dt of mod u k squared, okay, and that is the equation. Well, I divide by 2, then I get this equation. So, the nonlinear term, the one which was u dot grad u, in the energy equation there will be another u, I am multiplying another u, right, this u star k. So, it happens to be k dot u q u p dot u k star, imaginary part of this. So, this is the, so the k mode is getting energy from other modes by nonlinearity, right. So, we also make a triad like that, k p q, right, p plus q is equal to k. So, here this k mode is getting energy from u p and u q. So, the u p is giving energy to u k, okay. So, that is the energy going to u k. So, there is a formalism, okay, which is useful, but we do not need to get into that. So, this guy is giving energy, but what about this guy is like a mediator, okay, but we do not need to get there for today's lecture. So, this is the equation for the energy transfer by nonlinearity. This is the energy coming into k from external force. So, we write this in fact as f of k, f u. So, this energy injection per unit time to wave number k from external force, and this is a viscous dissipation. So, there is a loss because of viscosity, and that is a viscous dissipation term. So, every term has a name, this is called TUK, okay. So, this is nonlinear transfer term, and this is the injection rate due to force, external force, and this is the dissipation. So, DUK is positive, the minus sign is outside, okay. So, dissipation rate, these are all per unit time, okay, this d by dt is here, so per unit time.